Imagine spending like the last 10 years of your life mastering how to build these perfect, unbreakable steel bridges.
Right. Total precision.
Exactly. Every single beam is mathematically calculated. Every rivet is accounted for. You know exactly how much weight it can hold. And if something breaks, you know exactly which structural support gave way.
Because it's a closed system.
Right. And then tomorrow, you show up to the job site, and they tell you to build a bridge out of a completely new material. A material that, I mean, it literally randomly changes its shape whenever you look at it.
Yeah, that's a brilliant way to put it.
If you are a traditional software engineer looking at the current state of artificial intelligence right now, that is exactly what your career feels like.
It is a total untethering from the reality you were trained in.
Yeah.
You spend your entire career in a deterministic world, right? X goes in, Y comes out. Every single time. And there is a deep psychological comfort in that predictability.
There really is.
Yeah.
And right now, there is a very good chance you're listening to this late at night. The rest of the world is asleep. You've got your IDE open, dark mode enabled, maybe a lukewarm cup of coffee next to you.
A classic developer setup.
Exactly. And you are wrestling with this exact feeling. Because when you sit there staring at traditional code, there's this comforting rhythm. You write the logic, you pass the variables, and if something breaks,
Retrace the stack.
right, you find the exact line where the logic failed, and you fix it. It's binary, true or false. But the moment you step into the world of large language models, that comfort blanket is just ripped away entirely.
Yeah, you aren't just learning a new syntax here. It's not like, picking up Rust after years of writing Python.
Not at all.
You are having to rewire how you fundamentally define what software even is. I mean, it is a massive paradigm shift from rigid instruction to basically probabilistic suggestion.
Okay, let's unpack this, because bridging that terrifying gap is our mission tonight. We're doing a deep dive into the source material that really maps out this exact transition.
And it's a great source to pull from.
It really is. We're looking at episode 137 of the LLM Mastery Podcast. The episode is essentially a seasoned software engineer looking back on their own grueling transition into becoming an AI practitioner.
Right.
And when you look at how top engineers are making this leap, the very first massive shock to the system comes down to how we understand one single word, and that word is scale.
Oh, yeah. Scale is arguably the hardest conceptual hurdle for a veteran engineer to clear.
Really? Why is that?
Because their existing definition of the word actually works against them here.
I can completely see why, honestly. Let's look at it from a standard development perspective for a second. In traditional coding, scale is just infrastructure.
Exactly. It's plumbing.
Right. Like, if I have a web app and it's struggling, I might add 64 gigs of RAM. I might spin up more AWS server space. But doing that doesn't magically write a brand new complex checkout feature for my app, right?
No, of course not.
Adding more compute just runs the exact same code I already wrote, just faster, or, for more concurrent users. But in the deep learning space, scale operates completely differently.
It's a totally different beast.
It is.
Yeah.
Adding strictly quantitative changes, meaning just feeding in more data and throwing more compute at the training process, somehow produces entirely new qualitative capabilities.
What's fascinating here is the crucial shift is separating the concept of hardware infrastructure from what we call pattern density.
Pattern density. Okay, break that down.
Well, in traditional software, you, the human, are hard-coding the logic. The machine is just a dumb executor of your brilliant rules, right?
Right. It just does what I say.
Exactly. But in deep learning, you aren't writing the rules of the task. You are writing the architecture that searches for the rules.
So the architecture is essentially a blank net being dragged through an ocean of data.
That's a great way to visualize it. When you increase the scale, when you feed a model 1 trillion words instead of 1 billion words, and you give it 10 times the parameters to hold the relationships between those words, the model isn't just doing a simple task faster.
It's doing something entirely new.
Right. It suddenly has the resolution to map relationships in a high-dimensional space that it simply could not see before.
Wow.
At a certain point of data saturation, the model starts to abstract. It realizes that if you take the concept of king, subtract the concept of man, and add the concept of woman, the closest resulting concept is queen.
Wait, let me stop you there. Because the traditional engineer in me hears that and thinks, okay, someone programmed a relational database to link those words, but they didn't.
Nope. No one explicitly programmed that logic.
That is wild.
It inferred it because the sheer crushing volume of data forced it to find an efficient way to compress human language. And it turns out the most efficient way to compress human language looks remarkably like reasoning.
You know, it's less like upgrading a digital camera to get a higher resolution picture, and more like physics.
How do you mean?
Well, if you have one water molecule, it's just a particle, right? It doesn't really do anything.
Right.
But if you put billions of them together, you suddenly get emergent properties. You get wetness.
Yes.
You get waves.
Yeah.
You get ocean currents. The scale literally creates a new physical property that did not exist in the individual parts.
That is the perfect analogy, emergent properties. You have to stop viewing scale as just the plumbing and start viewing it as an active, creative ingredient in the software itself. I mean, the wetness didn't exist until the scale demanded it.
Right. But if scale births these incredible new capabilities, how do we fix it when those capabilities misfire?
That is the million-dollar question.
Because relying on emergent properties to solve your problems creates an entirely new set of headaches. Headaches that your traditional debugging tools are just completely blind to.
Totally blind.
If the model is just guessing based on a trillion data points, how do you even write a unit test?
You are hitting on the exact friction point that drives traditional engineers crazy. In the AI space, the hangover from the magic of scale can be quite severe.
Let's tackle the biggest headache first from our source material: the stubbornly persistent nature of AI hallucinations.
Oh, yeah. The elephant in the room.
It really is.
Yeah.
Even with all the evolving mitigation efforts we see in the industry right now, hallucinations just won't go away. So my initial theory, looking at this through a deterministic lens, is that we just haven't written a strict enough prompt yet, or, the training data is just a little too messy.
That's the logical assumption.
Right, like if it's hallucinating, it's a bug we haven't patched.
Actually, no. That is the traditional mindset talking, and it's the first thing that has to go.
Really?
Yeah. You can't prompt away a hallucination because hallucination isn't a bug. It's the exact same probabilistic mechanism that generates a brilliant insight.
Wait, explain that to the coder whose AI assistant just confidently invented a legal precedent that does not exist anywhere in the real world. How is that not a bug?
Think about the underlying mechanics. A large language model is, at its foundation, a next token predictor.
Okay.
It is calculating the statistical likelihood of the next piece of a word based on that massive high-dimensional map we just talked about. It has no internal ground truth. It has no foundational concept of fact versus fiction.
It just knows patterns.
Exactly. It only knows highly probable sequence of text. So when it hallucinates that fake legal case, it's not breaking. It is successfully generating a highly probable sequence of tokens that just happens to be factually incorrect in our physical reality.
But wait, what if we use something like retrieval augmented generation? RG is everywhere right now.
Sure, RG is huge.
Right, so we hook the AI up to a verified, encrypted database of real legal documents, and we force it to look at those documents before it speaks. Doesn't that patch the hallucination bug?
RG mitigates the issue, certainly. You are giving it a high-quality context window. But you haven't changed the underlying mechanism. The AI is still fundamentally guessing the next token.
Oh, I see.
If the statistical pull of its pre-training data is strong enough, it will ignore your pristine database and hallucinate anyway.
That's terrifying.
It is.
Yeah.
You cannot patch out the probabilistic nature of the model without destroying the very creative generalization that makes it useful in the first place. You can't fix the shape-shifting bridge because the material is supposed to shape-shift.
This raises an important question, though. How do we build around that? That is deeply unsettling for someone who spent a decade writing integration tests that demand a rigid true or false output.
This raises an important question about how we manage these traits. Absolutely. You are managing probabilities now, not eliminating errors completely.
And it's not the only sobering reality we have to face in this deep dive.
Yeah.
If fixing hallucinations is practically impossible, we also have to deal with the hidden physical toll of simply running these probabilistic guesses.
The environmental cost.
Yes, it is staggering. The power and water consumption required for these massive models is growing much faster than any of the efficiency improvements we are inventing.
And this brings us right back to the double-edged sword of scale. If the only way to get those qualitative emergent capability jumps is to exponentially increase the compute and the data.
Then you're locked into an exponential energy curve.
Exactly. The hardware efficiency gains, better silicon, optimized data center cooling, those improvements are linear. But the demand for scale is exponential.
So we are trading vast physical amounts of electricity and water for a system that still might confidently lie to us about a legal brief.
It's a brutal trade-off.
It really is. Which leads me to the ultimate question for the listener sitting at their desk right now. If we are dealing with stubborn, probabilistic behaviors instead of standard bugs, and the overhead is this massive, does your entire traditional toolkit become obsolete? Do you have to burn down everything you know and start from scratch?
The short answer is absolutely not. And this is perhaps the most reassuring revelation for anyone making this transition.
Which is fantastic news. You aren't starting from zero. The reflections from our practitioner explicitly list the traditional software engineering skills that transfer directly to AI work.
And they are crucial skills.
Absolutely. We are talking about deep systems thinking, your rigorous debugging methodology, your strict testing discipline, and your mastery of version control. All of that translates perfectly.
In fact, I would argue those traditional skills are what separate a tourist in the AI space from a professional. The theoretical researchers know how to build the model, but they often lack the discipline to deploy it safely.
But you do need to bolt on a few new paradigms. First, statistical thinking, and second, practical linear algebra.
Let's look at statistical thinking first.
Yeah, here's where it gets really interesting for me. Shifting an engineer's brain from else logic to maybe probably logic feels less like learning a new coding language and much more like moving from classical mechanics to quantum physics.
That's a profound way to look at it,
It
really.
feels accurate, right?
Yeah, definitely. In classical mechanics, you know exactly where a ball is going to land if you throw it. In quantum physics, you can't measure the exact position of the particle. You can only measure its probability distribution. That is statistical thinking.
So it's about ranges of outcomes.
Right. In AI, you can't write a unit test that says, if the user's prompt is exactly X, the model's output must be exactly Y, because the output might be slightly different every single time you run it.
So how do you actually test it? I mean, if a software engineer's entire job is enforcing reliability, you can't just throw your hands up and say, well, it's AI, let's ship it to production and hope it doesn't insult the customer.
Exactly. And that is where your veteran testing discipline comes in. You adapt. If we connect this to the bigger picture, instead of exact string matching, you build sophisticated evaluation pipelines.
Okay, what does that look like in practice?
Let's say you have a massive, expensive model generating customer support emails. You don't read them all manually. You take a smaller, cheaper, highly focused AI model and you program it to act as a grader. You give the smaller model a strict rubric, say, checking for polite tone and accurate refund policies.
Oh, I see. So the small model reads the output of the big model and scores it on a scale of 1 to 10.
Precisely. You test for semantic similarity. You test against boundary conditions to see if you can trick the model into breaking its own rules.
That's brilliant.
You are managing the chaos of the probabilistic engine by building extremely robust, disciplined, deterministic fences around it. Your systems thinking allows you to see the AI not as an infallible magic oracle, but just as one incredibly noisy, unpredictable component in a much larger traditional software architecture.
That brings the anxiety level down significantly. You're just containing the blast radius.
Exactly.
But we have to talk about the second new skill, practical linear algebra. I know the moment you say math, half the audience just broke out in cold sweat.
Oh, I'm sure they did.
If I could just call the OpenAI API, pass it a text prompt, and get a JSON response back, why do I need to learn linear algebra?
Well, you can just use the API if you only ever want to be an end user building basic wrappers. But to be a competent practitioner, to actually fix things when they break, or optimize a model for your specific company, you have to understand the medium you are working in.
And that medium is math.
Linear algebra is the language of high-dimensional space.
Okay, break that down for me. We talked earlier about the model learning that king minus man plus woman equals queen. How did linear algebra actually make that happen?
Think of a matrix as a massive spreadsheet of traits. The AI model doesn't understand English. It translates every word, every concept into an array of numbers, a vector.
Oh, I'm with you.
Imagine a massive three-dimensional graph. The AI plots the word dog and the word cats very close together on this graph because their numeric values for traits like has fur and is a pet are nearly identical.
It's literally plotting physical coordinates.
Yes. When you understand linear algebra, you realize the AI isn't thinking at all. It is simply measuring the physical distance between coordinates in a high-dimensional space.
Wow. So when people talk about attention mechanisms, which is the core technology behind transformers, they're really just talking about matrix multiplication.
That is all it is. An attention mechanism is just the model multiplying matrices together to figure out which words in a sentence are closest to each other in meaning, and therefore which words deserve the most attention.
That's it. Just multiplying grids of numbers.
That's it. If you don't understand those underlying matrices, you are just blindly tweaking dials on a black box, hoping for a better result.
But once an engineer visualizes that graph, the magic disappears. It becomes mechanics again.
Exactly.
You can read a dense new research paper, look at the math, and actually visualize the matrix transformations they're proposing. You see the gears turning.
It demystifies the entire field. It gives you control over the architecture.
Let's synthesize all of this. If a software engineer listening right now takes their hard-earned systems thinking, they actively embrace practical linear algebra without fear, and they fully accept that hallucinations are an unpatchable feature of probability, what is the timeline.
How long does it take?
Yeah. How long does it actually take to transition from an interested observer who just plays with an LLM on the side to a truly useful practitioner?
The timeline is both sobering and incredibly encouraging. Based on the practitioner's reflections we've been looking at, it takes an honest, intensive year of focused study.
12 months.
12 months.
And we need to be specific about what competent actually means at the end of those 12 months. It doesn't mean you can just write a clever system prompt.
No, not at all.
It means you will be able to build robust, secure production AI applications. It means you can take an open source model, download it, and fine-tune its internal weights on your own company's proprietary data.
Right. And crucially, it means you can read complex AI research papers and actually implement the experimental architectures described in them.
12 months to go from a deterministic web developer to an AI practitioner capable of implementing cutting-edge research. In the grand scheme of a 30-year career, that is a blink of an eye.
It really is.
And it puts the source material we've been referencing into an amazing context. Think about the journey this represents. This reflection we've been unpacking is episode 137 out of 144 total episodes in that LLM Mastery series.
That is a massive body of work.
Over 136 episodes, they've covered literally everything. From the absolute basics of how a transformer works to the messy, real-world realities of government regulation. From the deep math of multi-headed attention to the hyper-practical challenges of getting a model to run locally on a smartphone.
They really covered the whole landscape.
And the very next episode, tomorrow, is their finale, creating a practical roadmap for where the industry goes from here.
It is a testament to the fact that this field, despite how wild it seems, is entirely knowable. It feels overwhelming right now because of the sheer volume of noise and hype.
Oh, the hype is deafening.
But when you break it down systematically, architecture, probability, evaluation, it is highly learnable for someone who already knows how to think like an engineer.
So what does this all mean for you? The person listening right now staring at that dark mode screen. It means the bridge between traditional software and artificial intelligence is not nearly as broken as it might seem.
Not at all.
You weren't throwing away your career. You were simply porting it over to a new operating system. One that requires a little more math and a massive tolerance for ambiguity.
The software engineering industry desperately needs people with this dual mindset. I mean, the AI space is currently flooded with theoretical researchers who build incredible engines, but they need rigorous systems thinking mechanics to actually put those engines into cars that are safe to drive.
Which leaves us with one final lingering thought to ponder tonight.
Let's hear it.
We've established that the transition is entirely possible. If it only takes a year for a traditional engineer to master the AI toolkit, to bolt statistical thinking onto their existing debugging skills, then the bottleneck in this industry isn't human talent anymore.
Oh, that's a good point.
What happens to the broader tech landscape when millions of traditional developers suddenly realize they already possess the hardest half of the required skills and they all pivot at once? The talent bottleneck just vanishes.
It does.
But the energy and compute bottlenecks we discussed, those remain. The real question isn't whether you can learn to build these incredible probabilistic systems. The question is whether the world has enough electricity and data to feed the things that millions of newly trained engineers are about to unleash. Think about that next time you hit compile.